For centuries, humans believed in a static, unchanging universe. This view began to shift in the early 20th century with groundbreaking discoveries. In 1929, Edwin Hubble made a revolutionary observation that changed our understanding of the cosmos. He discovered that galaxies are moving away from us, and the farther they are, the faster they seem to recede. Hubble's discovery was based on the analysis of light from distant galaxies. He observed that the light waves were stretched, shifting towards the red end of the spectrum. This phenomenon, known as redshift, is similar to the Doppler effect observed with sound waves. Hubble's observations provided the first concrete evidence that the universe is not static but expanding. This expansion implies that the universe was once much smaller and denser, laying the foundation for the Big Bang theory. Edwin Hubble's observations of distant galaxies revealed a startling truth. The universe is not static but expanding. Hubble noticed a peculiar phenomenon. The light waves were stretched, their wavelengths shifted towards the red end of the spectrum. This stretching, known as redshift, is analogous to the Doppler effect observed with sound waves. Imagine an ambulance siren approaching. Its pitch sounds higher as the sound waves are compressed. As the ambulance moves away, the pitch lowers as the sound waves stretch out. Similarly, light waves from receding galaxies get stretched, causing a redshift. Hubble meticulously measured the redshift of numerous galaxies and correlated it with their distances. His groundbreaking discovery, now known as Hubble's law, established a direct relationship. The farther a galaxy is from us, the faster it is receding. This relationship implied that the universe is expanding uniformly, with galaxies moving apart like raisins in a rising loaf of bread. The cosmic puzzle. Expansion speeding up. While Hubble's discovery established the universe's expansion, subsequent observations in the late 20th century unveiled an even more perplexing phenomenon. The expansion is not constant, but accelerating. This unexpected discovery, made by two independent teams of astronomers in the late 1990s, sent ripples through the scientific community. The groundbreaking observations involved studying distant supernovae, specifically a type known as Type Ia supernovae. These stellar explosions serve as standard candles in astronomy due to their consistent intrinsic brightness. By measuring their apparent brightness, astronomers can accurately determine their distances. Surprisingly, these distant Type Ia supernovae appeared dimmer than expected based on their redshift and the prevailing understanding of a uniformly expanding universe. This discrepancy indicated that the expansion of the universe was not slowing down due to gravity, as previously assumed, but instead speeding up. Dark energy, the enigmatic force. The accelerating expansion of the universe suggests a mysterious force at play, counteracting gravity and pushing galaxies apart with increasing speed. This enigmatic force, termed dark energy, constitutes a significant portion of the universe's total energy density, yet its nature remains one of the biggest mysteries in modern science. Dark energy's properties remain elusive, but its influence on the universe's expansion is undeniable. It's thought to be a uniform energy field permeating all of space, exerting a negative pressure that drives the accelerated expansion. Unlike gravity, which pulls matter together, dark energy acts as a repulsive force, stretching the very fabric of space-time. While we don't fully understand dark energy's origin or composition, several theories attempt to explain its nature. The discovery of the universe's accelerating expansion relied on observations of distant Type Ia supernovae. These stellar explosions, occurring in binary star systems, serve as reliable standard candles for astronomers. Type Ia supernovae explode with consistent intrinsic brightness, ideal for measuring cosmic distances. Comparing their apparent brightness to intrinsic brightness helps determine distances. In the late 1990s, two teams studied distant Type Ia supernovae to measure the universe's expansion rate. They found these distant supernovae were dimmer than expected. This indicated the supernovae were farther away than predicted. Section 7. Visualizing the invisible, understanding dark energy. Imagine a balloon with dots drawn on its surface representing galaxies. As you inflate the balloon, the dots move apart, simulating the expansion of the universe. Now imagine that the balloon's expansion is not only continuing but also speeding up. This is the effect of dark energy. Dark energy, however, doesn't work like the air pressure inflating the balloon. Instead, it's more like a property inherent to the balloon's fabric itself, causing it to stretch at an accelerating rate. This analogy helps visualize how dark energy, uniformly distributed throughout space, drives the universe's accelerated expansion. While these analogies are helpful for visualization, they have limitations in fully capturing the complex nature of dark energy. The accelerating expansion of the universe driven by dark energy has profound implications for the future of the cosmos. As the expansion continues at an increasing rate, galaxies will be pushed farther apart, eventually becoming isolated islands in the vast expanse of space. The increasing distances between galaxies mean that over time, less and less of the universe will be observable to us. The light from distant galaxies will take longer to reach us, and eventually the expansion will be so rapid that light from some regions will never reach us at all. This cosmic isolation has significant consequences for the future of life in the universe. As galaxies drift apart, the opportunities for interaction and exchange of matter will diminish.